So, good afternoon to all. We are pleased to welcome Dr. Kamel Mazhouda, a Tunisian mathematician whose work lies at the heart of analytic number theory. He specializes in L functions, the generalized Riemann hypothesis, and Lie coefficient. Dr. Mazhouda earned his PhD in mathematics in 2011 from the Faculty of Sciences of Tunis, followed by his habilitation. He currently serves as a lecturer at the Higher of Institute of Applied Sciences and Technology of Sousse, and is affiliated with two French research institutions, the Research Institute in Limoges and the University of Valenciennes. His research focuses on the zero of L functions in the Selberg class and the variant equivalent formulations of generalized Riemann hypothesis. Dr. Mazhouda has published extensively and actively collaborates with researchers across Europe and North Africa. We are honored to have him with us today to share his insights into one of the most profound problems in mathematics. Thank you again, Dr. Mazhouda, for accepting to be our speaker in this webinar. And please, you can start your talk.
Okay, Professor Rafiq. First, many thanks to the organizer, mainly to my friend, Professor Rafiq Agash, for this invitation, who gave me the opportunity to speak about my recent work. My talk is part of analytic number theory and is mainly about the superzeta function on function field and some relation with the liquid. My talk contains four parts. In the first part, I will speak about zeta function on function field, some definition and property and notation. Then I will speak about Lie criterion and the Lie coefficient on function field. And the main part of my talk are the superzeta function on function field, where I will speak about two types of superzeta function, the superzeta function of first kind and superzeta function of second kind, and I will try to make a relation with the Riemann hypothesis and liquid. Let's begin with the first part. I will define the zeta function on function field. Let K be a function field of genus G with a finite field Fk. We define the function Zkx by two ways, by this power series or by a product over prime ideal D, where Cn is defined by the cardinal of this set. This function is a rational function, which equal to Ldx, the polynomial Ldx over 1 minus x times 1 minus qx. We remark that this polynomial is of degree dg, and the special value of this polynomial at x equal 1 is of interest. We call this special value the class number of K, and we do not it by hk. The complex number alpha 1, alpha 2g are algebraic integer and can be arranged so that their product equal to key. We recall that the Riemann hypothesis for function field proved by André Weil state that all alpha g are of absolute value square root of key. Those coefficients.
Sorry, a question, please, Dr. Mazhouda. What is Q and what is G? What represents Q and G, please?
Le Q, ça c'est le module.
Sorry.
It's the module of alpha G.
Okay, the norm of alpha G.
Voilà.
And G?
C'est G, c'est between 1 and 2G. and 2G, ça c'est genre of the function field K. Voilà.
Okay, thank you.
Okay.
But because Q, sorry. Can you come back to the previous slide, please?
Can you?
Can you come back to the previous slide, please?
Okay. Bon, now we define what we call the classical zeta function.
Sorry, Dr. Kamel.
Oui.
Dr. Wissam asks you to come back to the slide number 3. He has a question.
Okay.
Slide. Yes.
Okay.
Okay.
In the third equation in blue,
Yes.
with the finite field FQ, we still don't understand what is the Q.
FQ is a finite field which is defined by the power of key.
Okay. Okay. The expansion with the powers of
Well, yes. Now we to find the classical notation of the zeta function, we will replace x by q power minus s to find the classical notation, and we define in that way the zeta function on the function field by the series which is converged for real ds bigger than 1. This function has analytic property like the Riemann classical zeta function. This function is a monomorphic and have a monomorphic continuation to the whole complex plane C with the two pole 1 plus k 2pi over log d p and k 2pi over log d k, and mainly satisfy the function equation, this function equation. But if we put lambda k s equal to k power g minus 1 s zeta k s, then we remark that this equation function is simple. And but this function is not an entire function, since it possesses pole. So we will construct another function which is entire and of order 1. So we will multiply this function lambda k par daughter factor, and we get which we call the completed zeta function xkds. And xks verify the same function equation and simple, and we can see that from this simple function equation that there is a symmetry of the zero of the zeta function on function field. There is two symmetry. There is symmetry respect to the real axis and symmetry respect to the line real ds equal to 1/2. And if we see the representation of the zeta k by a series which converge for real ds bigger than 1, we can conclude that this function not vanish for real ds bigger than 1. And by the function equation, we can conclude also that not vanish for real ds bigger than 0. So all the zero of this function are located in the critical bound between 0 and 1. And from the function equation, we can see that are symmetric with real ds equal to 1/2. And we can state in another form the Riemann hypothesis. The Riemann hypothesis now states that all the zero are of real part equal to 1/2. And we have explicitly those zero. We can find it if we take and put zk, the set of all zero row of zeta k, we can see that this set contain all zero written in the form 1/2 plus this term, and we can see are all located in the critical line real ds equal to 1/2. So they verify the Riemann hypothesis. We can state also an asymptotic formula for the number of the zero if the imaginary part of each zero is located between minus t and t. So the number of zero is equal to 2g log p over p times t plus another function which is bounded by minus 2g and 2g. Okay, now we pass to second part. We will speak about a first reformulation of the Riemann hypothesis. But I will begin by recall the Lie criterion in the classical case. The classical case means that I will take the completed Riemann zeta function. The completed Riemann zeta function is defined as below. So the Lie coefficients are defined by two ways. By the first way is n derivative of s power n minus 1 log cs at s equal 1, or also defined by sum over non-trivial zero of the Riemann zeta function. Also, we can define those coefficients by the Taylor coefficient of the derivative of the function phi, where phi is defined by two ways: the function c of 0.1 over 1 minus s, or c s over s minus 1. Why these equalities? This equality comes from the function equation. So, Lie in 1997 proved that the Riemann hypothesis is equal to the positivity of the coefficient lambda n. This criterion is extended in 24 by Lie for the directly L function, and with Sami Omar in 27, this criterion also is extended to Selberg class in 2019. In 2019, this criterion is extended to the function field, what I will speak today. Now, we define in the same way the Lie coef on function field by the same formula. Lambda Kn is equal to the sum over 0 of the zeta function on function field. And we remark that the set of 0 are verified zk equal 1 minus zk equal also 1 minus the conjugate of zk. So we can deduce that all coefficients are real and verify this equality. And with Smajlovic in 2019, we extended this criterion to the function field. The main question posed now: why we try to find this criterion function field? Because the Riemann hypothesis holds true in our case. So what importance of this criterion in function field? Our goal is not to just write this criterion on function field, but to deduce that since the Riemann hypothesis holds true in our case, so we can deduce many interesting results about for example, the invariant of the function field K, or some sums on function field. We will deduce all those results mainly from the positivity of the coefficient of Lie. To do so, we recall some property of the completed Xi function on function field. This function can be written as a Hadamard product as follows, but using the functional equation. And if we assume that those functions not vanish at 1/2, we can write this Hadamard product as follows. That means we can just take the product over the when the imaginary part of H0 is positive. But this condition, why we choose this condition? If we remark here that if delta G equals 0 and K equals 0, you remark that 1/2 is 0 of the zeta function on function field. So what to do if 1/2 is 0 of CK? In that case, instead of working with CK, we will work with another function, FK, which equals to CK over S minus 1/2 power n, where n is the multiplicity of H0. And we can conclude now that the new function Fk is not vanishing on S equal 1/2 and have the same 0 than Xk. So for this reason, we can assume always that 1/2 is not a 0 of Xk. Another thing to define, we can also prove that the Lie curve are also like the classical case. In the case of the Riemann zeta function, are also the coefficient in the Taylor expansion of the derivative of the logarithmic derivative of the function Xk at 0.1/1 minus z. In 2019, with Smantlovich, also we proved that we can express those coefficients at the nth derivative of this function when z equals 0. And we, in that case, we found that the Lie curve on function field satisfies the same property as in the classical case. But what new we can deduce from those coefficients? The first result in 2019 with Leilas Majlovich, we give first an arithmetic formula for those coefficients. Also, we prove an integral and a summation formula for those coefficients, and where here En and Tn are which we call the Chebyshev polynomial of the first and second kind. Also, we have proved an asymptotic formula for the coefficient lambda Kn.
Sorry, Dr. Wissam, Dr. Kamel. We don't see the last line of your slides. Can you choose masque? Yes, choose this.
Voilà.
Yes, okay.
Okay. Donc, we have proved arithmetic, integral, summation formula, and also an asymptotic formula. We see that for large enough n, we see those coefficients are equal to G log the key n plus Pt to the n. As application of those coefficients, the first application, if we choose n equal 1, we can give the first Lie coefficient is given by log the key, the derivative of L at t equal 1 minus G, using mainly the integral equation of the coefficient lambda Kn, we can prove a bound for a special value of the derivative of L at t equal 1. We remark that for key enough, large enough, this special value of the derivative of L at t equal 1 is equivalent to 2g hash k. That is mean that special value of the derivative of the polynomial L can be expressed uniquely by the invariant of the function field K. If we use instead of n equal 1, n equal 2, that means if we use the second Leak wave, we can give an equivalent of the second derivative of the polynomial L at t equal 1, and we can prove which is equivalent to 2g square 2g hash k. Also, this special value is expressed mainly in terms of the invariant of the function field K. Another application of the Leak wave, to do so, we define what we call gamma n, are the coefficient in the Taylor expansion of the derivative of the polynomial L at t equal 1. For n equal 1, we can use the summation formula if we replace n par 1 and gamma par its expression. We found the first equality lambda k1 is equal to 4 log square of log q times this series. And now we know that the first coefficient can be written using the derivative of the polynomial L at t equal 1 minus g, which we also can be expressed in terms of the coefficient gamma 0. So with Leyles-Matulovich, we have deduced the interesting summation formula, which is valid for all integer p bigger than 1. We can deduce many other interesting formula for bigger n. That means we can find other summation formula, or we can give some special value of higher derivative of the polynomial n. Okay, for the third part of my talk, and the main part is the Superzeta function. The Superzeta function are introduced mainly by Millin in 1917. Millin considered and defined a class of functions and those functions are defined by Z0 of the classical zeta function. And the first who gave the name of Superzeta is Voros in 2010. Called those functions are Superzeta function. The Superzeta function of the first kind, as I tell now, that are functions which are defined by the zero of the Riemann zeta function, but on function field, we will define a function which is defined by the zero of the zeta function, but now on function field. This function, we call it the Superzeta function of first kind, which is converged for real S bigger than 1, and when Z is in this set. The first result on the Superzeta function of the first kind is the analytic continuation. With Bllaca, Khmiri and Sodaïgui, we have proved that this function is analytic in all C. This can be deduced from the equation 5. A sketch of proof of this theorem. I will give just some line how we prove this theorem. First, using Voros argument, we can prove the first equation that the superzeta of the first can be expressed using this integral. And we replace zk2z by the derivative of the logarithmic derivative of the completed zeta function on function field. So we deduce that zk sz is now equal to this integral, and we add this constant term in the integral. And why this constant term? Because we can state a asymptotic formula for this, and to use integration par part. By integration par part and using the following asymptotic formula for the logarithmic for xk dz, we can prove that this integral is now hold true for real ds between 0 and 1. If you remark that this integral, this function, is valid for real ds bigger than 1, and now is hold true for real ds bigger than 0. Just we use it one integration per part. But now if we repeat integration per part and we use the following asymptotic formula for the n derivative of log xk dz, we prove that the integral in the equation 5 is holomorphic for real ds less than 1. So this integral is holomorphic in all C, and then the function, the superzeta function, on function field of the first kind has analytic continuation in all C. In fact, this theorem can be proved in another way, using what we call the Veil explicit formula. The Veil explicit formula are formula which relate a sum over 0 with a sum over prime. In fact, avec Bllaca, we have established those formula in the context of function field. So we can use those formula to prove again the analytic continuation of the superzeta function of first kind. But we can also try to prove this theorem in different way, a more easily, a more important. This third way to prove the analytic continuation is we will use what we call the Hurwitz zeta function. Let's recall that the Hurwitz zeta function, zeta hash sz, is defined for real s bigger than 1, and z is s private for negative integer by the absolute convergence theory, sum over 1 over n plus z power s. We know that this function has a meromorphic continuation to all S-plane with a single pole at S equal 1 of order 1 and with residue 1. And mainly we can see that some special value of this function at negative integer are expressed with the Bernoulli polynomial. And we will use this, mainly this equality, to give some special value of the superzeta function on function field of the first kind. Using the property of the Hurwitz zeta function, we can prove the following proposition. This proposition is proved with the Bllaca, Khmiri and Sodaïgui, that zk is equal to the following formula, which written in terms of the Hurwitz zeta function, which is defined for real s bigger than 1 and has analytic continuation for all s in C. I tell that this formula we can deduce some special value of the superzeta function, mainly when s is a negative integer. In this corollary, we will replace s by minus n, and we will get this formula. And when n is equal to 0, we can see that the superzeta function for n0 is equal to g. G is the genus of the function field K, which is an invariant. To prove this corollary is not very difficult. It's just replace s par minus n, and then use the following formula for the Bernoulli polynomial. And for the case n equal to 0, just we use the first polynomial or the two polynomial for n equal 0 and n equal 1, and replace in the formula to deduce that the special value of the superzeta function of the first kind at 0 and z equal to g. What we can deduce from this formula is if you see that this formula is now can be true and valid in all z plane. We compare with the proposition. This proposition is valid when z in the set x prime k, but now for n is a negative integer, this formula is valid for all z. Okay. Now we will make a relation between some special value of the superzeta function of the first kind and the liquid, or the what we call the Euler-Stieltjes constant. To do so, we note zk star n equal to zk n1. Just we will have some result about the special value of the superzeta function when s equal to positive integer now and z equal to 1. So we will define what we call the Euler-Stieltjes constant of the second kind. Those coefficients are the coefficient in the Taylor series expansion of the logarithmic derivative of the completed zeta function on function field around z equal 1. With the Bllaca, Khmiri and Sodaïgui, we have proved that zk star n is equal to g log dq plus the first Euler-Stieltjes constant if n equal 1, and if n bigger than 2 is equal to minus 1 power n minus 1, the n minus 1 Euler-Stieltjes coefficient. I will give some line or bien sketch of proof of this theorem. To prove this theorem, just we take the Euler product. Okay, I will return to recall the Euler product. Well, here the Euler product given by the formula 1. Okay. Now, okay, donc we take this Hadamard product for the completed XC function, and we make derivative. So we can conclude that the superzeta function of the first kind when s equal n is given by the following formula, and from the function equation, we can deduce that these zero are invariant by the map rho and 1 minus rho. So we can state a relation between the superzeta function at s equal n and z, and s equal n and 1 minus z is this given by the mainly by the simple function equation. So by the definition of the state constant, the Euler state constant, which are the and derivative of this function, we can deduce our theorem. But this theorem can be reformulated or rewritten in another way. With Bllaca, Khmiri and Sodaïgui, we have expressed the function zk star n in another way. So just if we compare this proposition and this theorem, just we try to write in another way the n minus 1 Euler state coefficient, and we will express it also in using the other Euler state constant. To do so, we will use this relation. In fact, using a result established by Bllaca, Khmiri and Sodaïgui, we can express this sum over 0, 1 over rho power n in terms of the liquid. And this is not very difficult, just we use the definition of the liquid. And now, using the symmetry, zk equal to 1 minus zk, we can write the function zk star n in terms of the liquid. But the liquid with Bllaca in 2021, we have expressed those coefficients, those Lie coefficients in terms of the Euler state constant. So if we replace lambda kg by this expression, and we use that this sum is equal g log dk if n equal 1 and 0 if n bigger than 2, we prove in another way the special value of the superzeta function of first kind when s equal n. Okay. Now the last part of my talk is about another type of superzeta function. It's we call superzeta function on function field of second kind. To do so, we recall that all zero of the zeta function on function field can be written in this form, 1/2 plus e 2 kg, where 2 kg is given as follows. So the superzeta function of the second kind are defined by the following equation. And also from the function equation, we can see that this function is invariant when we replace t par moins t. Also, we can write it in another way. That means that we can write it on the zero of positive imaginary part. With Bllaca, Khmiri and Sodaïgui, we also proved that this function it's defined for real ds bigger than 1/2, but has a minimorphic continuation to all s in C, with simple pole at 1/2 minus m, and the residue given as follows. Also, we have proved some special value of this function when s equal m and t together equal 0. If s equal m and t equal 0, we have the following formula. Here the psi denotes the d gamma function. Okay, but the main result of our paper is the relation between some special value of the superzeta of the second kind and the Lie coefficient. Here we consider the special value of the superzeta at positive integer, and we take t equal to 1/2, and we will call it also zk star m. If we assume that xk 1/2 not vanishing, so we can express this function in terms of the Lie coefficient. And inversely, we can also express the Lie coefficient in terms of zk star m. To prove the two equality, in fact, I will prove the first, but the second is not very difficult. We will use some algebra to prove the second. In fact, we write this as a matrix. We found that this matrix is a triangular matrix. So to write the inverse, we need to inverse the matrix founded. But here in my talk, I will just give an idea how to prove the first equality. From the expression of the 0 of the zeta function of function field, we can see that rho times 1 minus rho is equal to 1/4 plus square of 2 kg. So the superzeta function of the second kind at s equal m and 1/2 can be written as this sum. But using one equality of Voros, Voros proved that we can replace 1 over rho times 1 minus rho power m by this sum. This means that the binomial coefficient 1 over 1 minus rho n plus 1 over rho power n, and using this equality, we give this equation. But if we recall that from the function equation that there is a symmetry, zk equal to 1 minus zk, that means that we can replace 1 minus rho by rho. So zk star m equal to 2 sum and will be expressed using mainly the sum over 0 of the zeta function on function field. But this sum, we know how to express this sum in function of the Lie curve. This result can be deduced easily from the definition of the Lie curve. The sum over 0 equal to this sum which we found is here the Lie curve. And if we replace, we find that the function zk star m equal to sum over g, sum over n, the product of binomial coefficient and the Lie curve. And to prove our equality, we need to use the following identity between sum of product of binomial coefficient, which equal to L plus 1, P plus 1, and then we replace K par pi n, Q pi g, P par pi n plus g minus 1, and L pi 2n minus 1. So we get that this sum of product of binomial coefficient equal the simple binomial coefficient 2n n plus g, but we can use the property of binomial coefficient is equal to 2m minus n plus g, which is equal to 2m n1 minus g, and this proves the first equality. Here in my talk, I don't put the proof of the second, but as I tell, the proof is not very difficult, but use some algebraic computation using mainly matrix. Okay. In my talk, I have used 4 references. The first reference is a walk with Bllaca. The second reference is with Bllaca, Khmiri and Sodaïgui. Also with Bllaca, Khmiri and Sodaïgui. And mainly our paper with Smajlovic about the Lie curve. But before finish my talk, here in my talk, I speak about mainly the Riemann hypothesis, which is proved in the case of the function field. And we have proved analogous or reformulation of this hypothesis, which is the Lie criterion. Since the Riemann hypothesis hold true, in our case, we have also the positivity of all Lie curve and the positive of Lie curve. With the positive, we have deduced many applications. But the main question is the Riemann hypothesis for other class of L function. For example, we speak about the classical Riemann zeta function. The classical Riemann zeta function, this problem was proposed by Riemann, and until now it's not proven. All mathematicians think that prove this conjecture or this hypothesis is very difficult directly. So mainly the number theorists think that we can find a reformulation of this conjecture more easily than prove it directly. We think that the easily reformulation of the Riemann hypothesis is Lagrange's reformulation. Lagrange proved that Riemann hypothesis is equivalent to that sum of divisor of n is less than hash n plus exponential hash n log hash n, where hash n is a harmonic series. But there is many other reformulation of the Riemann hypothesis. There is probabilist reformulation, there is algebraic reformulation, there is geometric formulation, there is integral formulation. For example, also I see that Balazar, Sousse, and Jawher prove that Riemann hypothesis is equivalent to the that this integral is equal to 0. So the body of the Riemann hypothesis, the importance of the Riemann hypothesis, that there is a variety of equivalence formulation. We think that each mathematician can work on this problem without leaving his specialty. That means that number theorist can work on this hypothesis, probabilist can work on this conjecture and hypothesis, but which is the best to try to solve this problem. I don't know the how to do this, but for the importance of this conjecture, and before I finish my talk, I will recall what David Hilbert say. David Hilbert say that the first question would be, has the Riemann hypothesis has been proved if he were to waken after having slept for 1,000 years? To see the importance of this hypothesis, this conjecture. Also, I will recall also what André Weil say, because André Weil has proved the Riemann hypothesis on function field, but for other class of L function is still unproved. But he say that when I was young, I hoped to demonstrate the Riemann hypothesis. When I got a little older, I still had hope that I could read and understand a proof of the Riemann hypothesis. But when now, means that when he is old, now I would be happy to learn that there is a proof. I don't know. I am in what step. Thank you for your attention.
Thank you for you, Dr. Mazhouda, for this nice talk in this nice topic. And Dr. Mazhouda thinks that we can one day have a proof of Riemann conjecture, Riemann problem. Okay.
I don't know.
Okay.
We call it the millennium.
Okay.
It's the millennium problem.
Okay. Are there some questions, please?
May I start with the question?
Yes.
Could you please go to slide, Kamel, slide number 26?
20?
26.
26.
Anna.
Okay. Then in the first equation, you have already shown that lambda k are positive because you have an equivalence, the counterpart of Lie,
Yes.
Because of your zk. Then the lambda k are all positive, right?
Yes, because are equivalent to the Riemann hypothesis. The Riemann hypothesis in our case is hold true.
Okay. Then 27, please. Okay, in equation 14,
Yes.
between the parentheses, you're
Yes.
summing on k, right?
Yes.
You are summing something positive plus a constant.
Yes, because the case k equal to 0 must be alone.
No, I have a concern of the convergence of the what is between the parentheses.
Yes.
You are summing on k.
Yes.
which is positive plus a constant.
Yes, for k is plus constant.
Yes.
Yes, but
And
the
then
sum.
the sum
Yes.
is divergent. No?
Yes, plus positive. Yes, but
No.
k is here.
His question is that the sum from 1 to plus infinity of 1 over tau plus t squared
Yes.
power s can be equal to plus infinity, no? Because it is
No,
a sum, infinite sum of a constant.
no, it's a converge
The plus
because
is
here.
outside the sum, huh? The plus. Just
The second term, the sum of the second term, yes.
Yes,
yeah, yeah.
it's
Plus
a
is
constant.
outside. Okay, you understand.
Yes.
Uh,
This term is not depend on for k.
it's not within the sum.
Oh, okay, but in this sum is a converge. Is a converge because he is k square of k.
Yeah, I understand. Okay.
As we have real s is bigger than 1/2. Donc square of k we have k power 2s, and k power 2s is bigger than 1. So that series is converged.
Okay. Can it be helpful to have another look to your function in t? Just
Yes.
replace it by square root of t, and you get a Stiegler's transform of order s in your expression 14.
We replace t par square of t.
Yes, and you have a Stiegler's transform on the
Oh,
right.
yeah.
If you
I don't know this how to write this transform.
then your function in square root of t
Yes.
will be not only completely monotone, but also Stiegler's transform of order s.
Ah,
Does it somewhere in your calculus?
no, I don't. We don't replace t par square of t. Huh? Just
Uh,
we just we take some special value of t. Huh?
okay.
But treat this sum for all t. No, we don't have an idea how.
Then, if you allow me, then 29, please.
Yes.
29. Why 29? Okay. Thank you. I finished it. Thank you for.
Thank you, Dr. Wissam. Are there other questions, please? Okay, as mentioned in the work of your 1999, are there some connection between your results and the stochastic processes? For example, connection between the Superzeta function of second kind and some stochastic processes.
I don't have an idea about this, but if you have an idea, why not?
Okay.
Uh,
My question, my other question, why the Superzeta function of kind 2? What is the needed results from the of the second kind?
okay,
Why you said the second kind Superzeta function?
oui, yes, because we can express the coefficient, we can express the liquid in terms of this super zeta function.
Okay.
We can
Okay.
express that,
Mhm.
and yes, and our goal is to have the maximum of information about the liquid, and using the other formula, for example, using the other formula, if we have the another expression of lambda k in terms of the the superzeta function of the second kind, so we can get many result on function field.
Okay.
The sum and result in function field.
Okay, thank you. If you can go to slide, next slide, 13.
Okay.
13. Okay, you cannot, as done for lambda k1 and lambda k0, using the same techniques, you cannot obtain an approximation of lambda kn for all n for any fixed n.
An approximation. For the derivative.
Yes.
Oh, the problem that for the higher derivative is the estimation of this integral. It's not easy, but because here we try to find the bound of this integral. So we need to bound the Chebyshev. We use the maximum of information about the Chebyshev polynomial. For higher derivative, the computation is not easy. That's why we just give that for n equal 1 or n equal 2, we can see and find an explicit formula easily.
Okay.
But my purpose is not to give the all special value of the or all the derivative, but to show that a good how to express this in English, to good use of the of those formula of the Leak wave, we can deduce many results in function field.
Okay. Thank you. Are there other questions, please? Yes, Dr. Fathi.
Some comment. Can you just open the camera, please, for me?
You can ask to start.
Again?
You can open it. No, Kamel. Please share the slides. Okay. No. Yes. Okay. Sorry.
And I came half an hour late or 25 minutes because we have finals. But I really would have liked to be there from the beginning. I really appreciate this talk. It was really nice, even though I could not attend the first 25 minutes. I would love to see the video and the full slides. I thank the professor and you, Professor Rafiq, for this beautiful presentations. And I'll be pursuing this subject with you both, perhaps very soon, inshallah. I don't have some specific comments at this point, but I will have probably in a week or two, inshallah.
Inshallah. Thank you, Professor Fathi.
From Kuwait, I salute you.
Okay. Welcome.
I salute the Tunisian team that is always ready and able to formulate and do these occasional webinars, etc. Al-Khwarizmi.
Thank you.
Thanks.
Just last remark, Dr. Kamel, in the first slide. Okay, today is 13 May and not 14. Just 13 May today.
Okay.
Okay. Are there other questions, please? Okay.
It's the last full moon day. Of the what's called the white days. It's the last one, the third one.
Okay.
Yeah.
Okay. If not, we have to thank again Dr. Mazhouda for this nice talk, and see you next week with talk number 21 for this academic year, and it will be the last talk for this session. Thank you again, and see you next week.
Okay.
Take care.
Thank you.
Thanks.
Thank you.
Thank you very much.